Hi everyone. Uh, so this is a series of 3 to 4 lectures where we will mainly talk about learning augmented algorithms and its application in gaming. So first I will introduce you to learning augmented algorithms. Learning augmented algorithms are also known as algorithms with predictions. So since nowadays we have lots and lots of data that are available for like any application that you can think about, right? We have lots and lots of data. So what we want now is that we know that our traditional algorithms that we study in our classes or in our colleges, they don't use this data, right? But can we use this data in our traditional algorithms, or can we just modify our algorithm a bit using this data that is available to come up with more efficient and more robust and more time efficient algorithms in general, right? So this is the basic theme of learning augmented algorithms or algorithms with predictions. Right? So let me just start and I will introduce you to things one by one. So what we'll do is that we will start with learning augmented algorithms. Okay. And I will introduce to you what this is. And as an application of this, we will show that for k means there are few algorithms. Basically, I will talk about two algorithms and will show some good bounds that we can have when we use learning augmented algorithms. But first of all, let me just introduce you what exactly learning augmented algorithms are. So in our traditional algorithm design, right? So traditional algorithm design, what we do is the following. So there is some problem that we want to solve. So we have some input for that. We design an algorithm and that would give us some output. So this is basically what we do. Our main goal here is to develop or to design a good algorithm which is whose time complexity or space complexity is tight enough, right? So this is what we do in our traditional algorithms. But as opposed to this, in learning augmented algorithms or algorithm with prediction, what we do is the following. Again, we have the similar kind of input. We expect some output of this algorithm depending on the problem. We will have some algorithm, but now this algorithm also gets as input some sort of prediction. Or you can, if you don't want to call it a prediction, you can assume that some more information is known, okay, which was not available in the traditional algorithm design, which is now known. So since we have this more information that is available to us, it is expected that we should get a more better result or we should have a more tight bound, right? We will explore this setting and I'll explain you with some examples in this first lecture that how this is possible, and then we will have some application of this that will show for games. Okay. Okay. So what is really the difference between these two kind of algorithms? So first of all, in traditional algorithm design, we do not use any historic data. So we do not use any kind of data, right? Historic data. But in algorithm with prediction, we will use data from the past, right? To design efficient algorithms, right? In traditional algorithms, normally the bounds that we get are worst case bound, or in sometimes we also get amortized bounds, right? In algorithm with predictions, we might end up with a bound which is better than the worst case. So we might get better than worst case bound, right? So this is in some sense going beyond the worst case, right? Okay. And in traditional algorithm design, when we are designing an algorithm, if some lower bound is known, with respect to that problem, we know that we cannot, whatever kind of algorithm you design, you cannot beat the lower bound, right? But in algorithm with predictions, since we know that we have now more information that we can leverage, it might be possible that we can go beyond lower bounds. So whatever the lower bounds are known for a specific kind of problem, in some cases we can even beat that lower bound. Okay? So this is in general, these things are uh, these are the differences between the two kind of algorithms, and we will start with some examples, and then I will show you what this exactly means and what is the notion of learning augmented algorithms. Right? So what would happen in generally with learning augmented algorithms is that with your algorithm, you'll also get a prediction. Okay, you'll also get a prediction with respect to your algorithm. Okay, so let us see what these predictions could be or like. So suppose I have this xy plane. Here I give my x-axis represents the prediction error that I will have. Again, the prediction error is defined on the specific kind of problem we are solving. So suppose in this zero means that my prediction has zero error, there were no error, and suppose n means all of my predictions were wrong. Okay. And suppose y-axis denotes the time complexity. Okay. It's just to set the notion of what is coming. Okay. Then suppose suppose you there is some problem A that we are solving, or there is some algorithm A in the traditional model, right? So that, and suppose this is the optimum time that this algorithm takes. So this is our traditional opt for a specific algorithm. So this is what the traditional optimum algorithm time look like. So this is generally the algorithm which is not using any kind of predictions, right? And suppose this is the online version of the problem. So this is the online cost that incur by that problem or by that algorithm. So maybe this is the online cost. Suppose we are in the online setting, right? Okay. So now, and here we are these two algorithms, they are just like traditional algorithms. They don't use any kind of predictions, right? What we want and what are the like, so these are the normal notions that is there in algorithm with prediction is that if I have some kind of prediction where all of my predictions are correct, that means my prediction error is kind of zero, right? So what I want with my algorithm with prediction, so suppose this with red we denote the algorithm which are algorithm with predictions. We want that my algorithm should be very close to the optimum, if not optimum. So if my prediction is zero, I want my algorithm to be very close to the optimum. Okay. This is in literature of algorithm with prediction is known as consistency or consistent. How consistent my algorithm is. Okay. Even if suppose my all the predictions they are wrong. So I got n predictions and all of them they are wrong. Even if my all the predictions are wrong, what I want from my algorithm that I designed that it should not be very bad. It can be as bad as the like worst case or online algorithm that is there. So even if my all the if my prediction error is n, I want my algorithm to be bounded by some quantity, maybe most of the time by the worst case online bound. Okay, so this is in general known as robustness of my algorithm. And in between, what I want is that with the number of uh, predictions increasing, I want my bound to increase with respect to the prediction error. So if the prediction error is high, the bound that I will get is also high. If the prediction error is low, the bound that I will get is pretty much close to the optimum. If my algorithm has this sort of relation, then this is known as smoothness of my algorithm. So in general, these are the three quantities that we need. Again, what is consistent? Consistent basically means you came up with an algorithm, you have some prediction, and suppose the prediction error is kind of zero or if it's like negligible, then your the bound that you will get that should be very pretty close to the offline optimum. Even if all your errors or all your predictions are wrong, then you should get a bound which is like very close to the online cost, worst case online cost, which is known as robustness. And in between, if your prediction error is increasing, your time complexity should increase as a function of the prediction error. Okay. So this is in general for any kind of algorithm with prediction model that we want this kind of guarantees. Okay. Now, to show you what this exactly means, I will come up with a very easy and known example that we all know about. So we will talk about binary search, right? So let's talk about binary search in general. So what we know about binary search? So we know that okay, suppose we have an array, right? So this array has some elements in them. Okay. So these are suppose the elements. Let's just give indexing 1, 2, 3, 4, 5, 6. And suppose there are some numbers in this array. Suppose 5, 8. Since we'll do binary search, this array is kind of sorted, right? 15, 19, 21, 28, 35. Suppose these are the numbers that we are. So in the traditional algorithm design, we know that the worst case time complexity of binary search is log of n, where n is the number of elements that you have, right? Now what you want to do, you want to show an example. This is just to set the tone of the and to give you some knowledge about how this prediction works. Suppose we incorporate some kind of prediction to binary search, right? So the first thing that we should think about is that what kind of predictions that I can have, or what are the normal in general prediction that I can generate, right? Even if in there would be some application where we don't have the predictions or we don't have that data, but is there something that we can easily generate and then we can use that as our predictions, right? So suppose I'm searching for some element, I'm searching for some item. So for with respect to this item, the prediction that I can have is that where this item lies in my sorted array. This could be my general predictions, right? So my prediction could be the index of the element, index where item lies, right? This is a very uh, the general kind of prediction that one can come up with. Okay? And let's try to use this prediction and see that if it helps in some way to get a better bound than order login for binary search. And we also know that order login is like kind of tight, right? Okay. So let's see this. Okay. So suppose let us just define few quantities now. You just wait for 1 minute. So suppose h is some function. Whenever I give a key to this function, it tells me a predicted position. So this is a predicted position that your item might lie in this position. Okay. And suppose T of Q is the actual position. So T of Q is the actual position where the item lies. Okay. And uh, mm, to give you an example, so uh, suppose you are working in a bookstore and someone comes and asks you that I need a book where the suppose the author's name is starting with B. So in your bookstore, you have many books it starts from A to Z. But since you know that the person asking for a name which starts with letter B, you will not go at the end of the shelf or you will not go at the middle of the shelf. Somewhere you know that okay where B lies, right? And you will have an appropriate or approximate position, which is like somehow denoting it as H of Q, and you will reach there. But it might be that instead of the shell B, you might have reached at cell D. It could be possible, right? Your prediction can be wrong, or it is wrong, but not by a factor of much, right? But since you are close to D, you know that okay, I have to traverse a bit towards my left and I will get B, right? So instead of doing binary search, since you had the knowledge upfront that you know where kind of B lies, you will get some advantage, right? Because you're not doing binary search. If you're doing binary search, then you will get some. You would have gone to some middle alphabet first, then you would have traversed in the way binary search does, right? But this should give you some help, right? So this is the motivation why suppose H of Q is. So H of Q tends to give you an approximate position which can be actually the actual position, and T of Q for an element Q is will give you the actual position that is there, right? So with this two, what we want our algorithm, so my algorithm could be such that okay, so whatever, so given a Q, I find HQ gives me some position which is a predicted position. I go in my array and I go to this predicted position, let me just denote this by P dash, and see if Q lies there. If I get Q there, then I'm done, right? If I don't get Q, then as without loss of generality, assume that Q is like less than P dash. So I know that I have this P dash here. This is for this is the P dash position where there is not, so in this position Q is not there. Q might be lying somewhere here. But now this is the distance that I have to traverse to reach to Q, right? So what can I do is one possible way is that maybe I will do a doubling binary search. So maybe what I will do, my algorithm is such that I will start with the position H of Q. Since I have to go left, if I don't find my element at, if I don't find Q at H of Q, I will go to H of Q minus 2. Then maybe I will go to H of Q minus 2 square. Again, I will go to H of Q minus 2 to the power 3 and so on till I find Q. Or maybe I will cross an element which was less than Q. In that sense, I will again come back to Q. But this is the operation that I want to do, right? So this is, suppose this is my algorithm. Then suppose NQ denotes the distance between these two quantities. So suppose NQ is a distance between HQ and the true value which is TQ, right? Then we can see that the cost that I will incur to search for Q with this prediction P dash that is given to me is 2 times log of H of Q minus P of Q, right? Why 2 times? Because if once I cross, then the maximum I can even search is TQ minus HQ again, log of TQ minus HQ again. So this is the bound that I will get in general if I go with this kind of predictions, right? And suppose if TQ, if the prediction that was given to me was actually the true predictions, then here what I will get is that if HQ equals TQ, right? Then in just order one time, I will get my element, right? So earlier it would took me login time, right? But now I can get the same element in order one time, right? So with just using prediction. Even if all of my predictions are wrong, I know that this quantity cannot be greater than n, right? Then also in worst case, I will get log n cost. Right? So with this simple example, we saw that so this satisfies both consistency and robustness, and in between it depends how far my elements are. It would also satisfy smoothness. Right? So now we have an algorithm which beats login in general using predictions, right? So this is what in general means using algorithms prediction, and we saw with this few example that it really works, right? So in the next lecture, we will talk about k-means, and we'll see some applications of k-means using prediction. Thank you.